Hi everyone, welcome to the 25th webinar in 12D's training webinar series. My name's Lisa Stewart. I'm the Marketing and Communications Coordinator here at 12D Solutions. 12D's training webinars showcase common industry challenges, taking a close look at industry best practices and how these can be implemented using 12D model software. The aim of these webinars is to upskill 12D model users and broaden their understanding of the capabilities of 12D model. We run these webinars regularly and record them for posting through our website and on YouTube. The first 24 webinars from this training series, as well as the first 25 webinars from our Industry Solutions series, are available on our YouTube channels if you missed those. During this live presentation, you'll be able to type your questions along the way. We'll put some instructions on the screen. We'll answer as many as possible throughout the webinar, and at the end I'll read out some of your questions to the presenter for his insights if there's time. Today's webinar, using the Apply function for non-road features, will be presented by David Owens, who has over 30 years of experience in the design of civil infrastructure, including roads, drains, parks, sports fields and landfill for Brisbane City Council, as well as more than 18 years of experience as a 12D user and 9 years as a 12D trainer. Today he'll be discussing the Apply MTF function in 12D model, which, as you'll see, can be used to model more than just roads. We can use it to model those features associated with the road. This webinar will look at a couple of these, such as retaining walls, bridge headstocks and abutments. Over to you, David.
Okay, thanks, Lisa. Afternoon, everybody. Yeah, I guess 12D model as a road design package is sort of pretty well established. It's almost old news in some ways. But recently I've had a few jobs on the go where I've had to model some of the other things around the road. Okay? So what I'm going to show today is just a couple of those things that I've had to deal with. The first one, flight of stairs, just as a simple little standalone function with a few sneaky little bits. Block retaining walls, but using the road functions to generate some data that I can use as a bit of a guide to design the wall heights. And the third one, spill-throughs, abutments and so forth, where I'm actually going to use the road models as reference data in the applying of those spill-through abutments. So sort of three different levels here. The first one, my flight of stairs, again, tried to keep as close as I could to standard drawings that are supplied by government authorities, in this case Brisbane Council. One of the things that really made this possible was the ability to have a negative offset when we're inserting links inside the MTF. Okay. So have a quick look at this one. I'll just got to pop over to 12D itself, just bear with me 1 second. Sticks right. Now these are real jobs that I've got on the go, so some of them are a little bit chunky and quite a lot of data in them, but hopefully it should go through fairly quickly. So you can see here the end result, what I'm actually trying to achieve is a true model, 3D objects of this flight of stairs, including the rails and posts and so forth. So how do we make this happen? Well, to start with, this whole thing is basically just one apply function to generate the stairs themselves and some super alignments to generate the handrails and so forth. But the stairs themselves are all linked to just one single alignment, which is sitting down at the base of the thing. Very, very simple alignment. It's just a short little straight line, just 1.5 meter long straight line along the lowest step, and just setting a height of that lower step to start from. And you can see there I've given the vertical geometry a bit of length. So the idea being that I can change the length of the horizontal geometry and still have some levels to use. And so that level's just sitting down at the ground, down at the base of the stairs down here. Inside the MTF file itself, again, there's probably nothing in here that you haven't actually seen. Oops, excuse me, wrong button. Nothing that you haven't seen before in some ways, maybe just using it just a little bit differently. So for example, made a huge use of the insert absolute command. So every one of these commands is setting up the risings and goings. for each of the steps. And you can see here in the rising insert, using a negative offset. So we get that little rake back on the front of the step, how it sort of leans back in, rather than just being a straight vertical. Again, so there's nothing particularly rocket science about that. There's just an awful lot of insert commands because in this case I've got quite a lot of steps. It's a pretty big flight, 18 steps in all. Okay. And also making use of the regions in these MTFs so I can collapse it up and keep everything manageable. And also at the end of this, just a couple of little modifiers, just inserting at a string which is matching into an existing footpath up the top. Okay. Another little sneaky bit that I did in this particular MTF was doing some inserts where I wanted to insert these posts for the handrails. So how I actually generate the posts I'll come to in just a little bit in a minute, but because we can put things on different layers within the MTF file now, I can insert these links of the offsets of where my vertical posts are going to be, and it doesn't interfere with the production of the steps themselves. They're on a completely different layer. Nothing interferes with each other. And creating the subgrade underneath the base, underneath these stairs, is no different to creating subgrades underneath the road, quite frankly. I've even called it boxing because it's essentially the same thing. And it's just inserting various links at widths and depths to just basically give the thickness of the concrete. Okay? So no different to as if you were doing the road, to be perfectly honest, in terms of how that works. Okay. Yeah, so basically a whole bunch of insert commands that just form a set of stairs. And then using the shape commands to link them all together and turn them into tri-mesh, so we get volumes and 3D objects and so forth. Okay. Now, it looks kind of pretty cool, I reckon. It looks very realistic. The handrails themselves are, again, just super alignments. Nothing mysterious in a super alignment. Just doing a couple of things that may be a little bit different. For example, in the horizontal geometry, there is a commutator which links the bulk of the stair rail to the original alignment, which is sitting down at the base there. But I've also just added a little floating section at each end to give myself enough distance to put in this extra little bit of vertical geometry for the little turnovers at the ends. Okay? So the commutator deals with the main bulk of the thing, and then these little extra bits for some extra vertical. Now, in the vertical geometry, that little floating line allows me to add in a very, very steep vertical section. You can see the grade there is incredibly steep. And a free circular arc of just a small radius, a 0.1 radius. And then I've just got some lines that are defining a height above the step treads as per the standard drawing. And quite frankly, one of those was enough to go to all that trouble for. So all the other handrails are all commutated of that one that's at the base on the left-hand side, the bottom rail on the left. So every other super alignment is, excuse me one second, handrail top left, that's what I'm looking for. So every other super alignment is using the same horizontal geometry computators, so it's relative to the lowest alignment when they're controlling the steps. But the vertical geometry is essentially computating with an offset grade to get the bulk of it. So I've still got to do the little vertical turn-outy bits. The offset struggles with things that are, for all intents and purposes, vertical. But for the bulk of it, where it comes up along the landing and then up to the top landing. Just a simple commutator as an offset with a height difference. And all the other 3 rails are done exactly the same way. So, because these are all computated together and all hanging off an apply function, if something should change, like say for example, the project manager decides he doesn't want a 1.5 metre wide set of stairs anymore, he'd prefer a 2 or a 3 metre wide set of stairs, then it's simply a case of going back to my base alignment that controls the whole thing, changing the length of that line to say 3 metres. Okay. So you can see here my alignment is now twice as long as it was before, and by throwing all this together now into a chain to resolve the MTF, to resolve the alignments, and to run my little macro to put the posts in, not a very big change, just a few things in there. When we run this one, it goes and rebuilds everything. Macro can't run behind the scenes, it's got to be interactive. So I can just process my little macro here, and I've now got a wider set of stairs with the posts and everything all linked in. Okay. So using our super alignments, using our computators to relate things together, makes the job really quite a breeze. So something that's not a road, but for all intents and purposes, using all the same techniques as if it was. Okay. I'll just the other one, and back to our slideshow. So the second thing, so that was just a real quick and easy one, just a bit of fun really. The second one, starting to get a little bit more involved, is what happens when we need to throw in a block retaining wall. And in my particular example, it's sitting in between split level carriageways. So it's going to be sitting in median. And so I'm going to be using the information out of the road models. And the key things to sort of look out for here, again, is this ability to create information on different layers. So I can model in the footings and the walls themselves in different layers. But probably the most important thing here is the ability to put named parts on our vertical geometry. I'm sure we've used named parts on horizontal before. You may not be aware that you can in fact do it in vertical as well. Okay. And that's what I'm going to be doing here. So into the block wall job. And again, as I said, these are real jobs, so they're a little bit on the chunky side, but bear with me. Okay. So when we've got split carriageways like this, I want to be able to generate surface models that I can use as a guide, as a bit of a help, but I don't want to interfere with the design itself, as in the finished strings that are going into production. So what I've done in this particular case, and there's 2 functions here, one for each side of the road. On the main carriageway down this side, I've thrown in a little group, a little region here in my MTF just called wall construction. And the whole purpose of this one is just to be able to generate a tin which describes effectively what I need to retain for the top level of the wall. So just use the limits of the length of the retaining wall strings themselves. There's just some super lines I've got in, I'll get to that in just a sec. Inserted a couple of links here at the kind of slope that I'm expecting to be coming down from this top level here. So I've got a slope that I want to just project out. I've made it nice and wide. I've given it 6 meters wide from the back of this curve here. So I've got plenty of tin to throw into my section view and start grading out my retaining walls. And then simply creating a tin from that model, or from that layer, I beg your pardon. Okay. So my layer of wall, got a couple of links in it, and just generating a tin from that. Okay. Exactly the same deal for the other side of the road. Yeah. group here, retaining wall construction. So I just inserted a link just coming up at 2% from the back of my curb. As we can see in the little cross section here, just coming up at 2%, just to give it a little bit of slope so it drains away, and created it in this case I only created the one link on the wall. The other link for my tin has actually come from the actual design strings themselves. Okay? So you can pick and choose what links you want to use to create a tin, which is really handy. Okay. So running those two functions, those two road functions, generates this blue tin for the top of my wall, this red tin for the base of my wall, and that's when it starts to get tedious. So we've got alignments running, one for the top and one for the base. Horizontally, they've got a 30mm offset as per the standard drawing. You can see, I don't know if you can see there, but there is just a little 30mm offset between the footing and the actual wall itself. So that's how I've done them horizontally. There's two alignments running through the middle of this median here. It's extremely tight, but there are two alignments in there. And it is then just a case of working your way through, putting in the levels, the step, the level, the step, the level, the step, however many steps you need to get your wall from the start to the end of the job. I'm hoping one day in the future there'll be a macro that'll take some of the tedium that out for me, but it's a work in progress. Okay, but anyway, the critical thing in this particular case, if I profile the top of the wall, because this is the main problem, this one. When it comes to running an apply function along something like a retaining wall, it's not all nice and smooth like a normal road where you've got everything's tangential, it all just flows from one to the other. Here we've got these almost instantaneous steps all the way along. So we need to have cross sections generated at all these points to get the actual true shape of the wall itself. Okay? If we just did it at a regular chainage interval, we might get one cross section here somewhere, another cross section up here somewhere, and it'll completely miss this big change in elevation at the top of the wall. So the trick in this case is lots and lots of named parts, and they're in the vertical geometry. Okay? Now, because there's so many of them, and I really hate typing, I've abbreviated them as much as I possibly can. I just call them H1, H2, H3, the H being horizontal. This is the horizontal part of the vertical geometry. There's no need to give a name to that little vertical part that's only 1 mil wide, but it's just excessive. Okay, so now that I've got all those named parts that I can refer to, in the apply many function, which I'm going to use to build the wall itself, I can put these all in the special chainages, so I get cross sections of all those points. Okay. So, looking at the wall itself, there is just one function. Now, if you just bear with me, I'll just put on some strings in my section view here, so I can bring up the MTF. Okay. So it's just one apply function to build both the footing and the wall itself, and everything is sitting on just the one side. So I've got the base of the wall, the blue one sort of sitting off here to the right, the red one to the left, and I am heading in that northerly direction, so the top of the wall is all on the left. Okay, that's what I was yeah. So the special chainages is the key to getting the shape right. And as you can see, I've got basically the start and end of every horizontal part of the top, the TW, the top of the wall alignment. All those named parts. Okay. So that did take a little bit of effort to get it in there, but once it's in there, the effect is really, very, very impressive. Okay. Now in the MTF file itself, when it comes to these retaining walls, obviously there's going to be different things happening with the footing depending on just how high the wall actually is. If it's a relatively small wall, you only need a small footing. If it's a tall wall, then footing needs to grow. So there's a little table in that standard drawing I was looking at before. So the way I've implemented that is to have a whole heap of decisions. Now these decisions are just testing the height difference. I'll just bring one up just to show. We're just testing the height difference of a link which is just sitting along the top of my footing, just as an insert command, just as if it was a row, just inserted a link. And the string that I'm comparing it with is that alignment that runs along the top of the wall. So effectively comparing the levels at the base of the wall to the top of the wall. By having these series of tests, when the height falls within a certain range, so for example, my very first test is if it's 1400 millimetre high wall. Any higher than that, then it's got to go off the proper structural design, but at 1400 I can just use my standard drawing. So if it falls within that level, then the go-to goes to a label which has called 1400 high wall, which is where all the insert commands then go for inserting the top of the wall links and also inserting the rest of the footing links. So I'm using different layers, the top of the footing, the base of the footing, top of the wall, base of the wall, that kind of thing. So I can then join up all the appropriate points into the shape command later. Yeah? And at the end of each of these, there's just a little go-to that says, all right, back down to the end of the MTF file, there's nothing else to do. So simply testing the height, comparing the top of the wall to the base of the wall, going to the appropriate region of the MTF to insert the links that are needed. Now, I did come across one little quirk in this. When generating the shape for the footings, it does get a little bit confused if links appear and disappear throughout the length of the apply. So when I had a footing which was very, very small and didn't need that extra heel built into it, I still had to insert the same number of links, but just effectively with zero height, zero width offsets, so that the actual physical shape that I'm left with was just a simple slab rather than a slab with that extra heel in it. So that was just one little quirk that I had to sort of work around. It threw me for a while. But yeah, so then there's just the shape commands to go through and pull those things together. But yeah, the critical things in there were the being able to do that height test between the two. So using the special changes along the top of the wall and then applying the function itself, I end up with a couple of tri-meshes, one describing the blocks themselves, another one describing the footing of our retaining wall here. And when we look at that in a perspective, we're getting, actually I might just make this a bit bigger because there's a fair bit of detailing. Quite a bit of detail then in how different footing sizes depending on just how high the wall happened to be at various places. So it's stepping in and out for the different width of the base. Got the heel built into it wherever it's needed. But occasionally, like right up the top where it starts to get quite a small wall, that heel just disappears, it's not needed anymore. So all the same links are there, just with a zero width, zero height. So that there. That's one little bit where it just got a little bit high on that changeover, needed the heel again. So. Yeah. One other thing which was a little bit tricky with this one was getting the overlap. Because where the wall itself steps up, the footing needs to project through just that little bit further so that we got something to tie the two different levels of slab together for the footings. And that was a simple little modifier which I've built into a snippet. But the basic modifier is using this concept of, I'll just bring the modifiers up again, and I'll just fire a blank one up rather than trying to read the snippet, because snippets are pretty ugly to look at. In this toHeights modifier, there is a type built into here where you can take the height at a particular position and push it forward. So there's a little snippet that runs at each of these locations where the footing steps from one height to another, again using the named parts on the horizontal geometry on the base alignment at that time. But we can take those levels, just finish that. I know it's not finished properly, that's all right. So we can take the level that happens at that point and just push it forward by another, I think that was about 300 mil in that particular case. Okay. A pretty accurate representation of footings and block walls. Okay. So the third one to look at, this one does start to get a little bit more involved because we're going to use the data coming out of the road functions, not just as a guide, but actually forming our computators and so forth. So moving on to the next one. Okay, so rocks built through is a TMR standard drawing, and I'm sure we all realise that there's a certain amount of artistic licence in standard drawings and enough unknowns for us to be able to sort of fill in the gaps with our own jobs, because they're all a little bit different. We've got different things we need to deal with. But this is trying to achieve the relationships that this drawing is describing in terms of hooking onto the height of our road level, finding a point down our 1 in 2 batter slope that intersects with the height required, that 1700 underneath the soffit, for an inspection ledge. So trying to generate this point was the one that I had to have some serious. I tried a few different options, but finally settled on something which I think works pretty well. Okay, now back to reality. Okay, so there's quite a few steps in this one, so just bear with me. So I decided that trying to do those build-through abutments from just one single alignment was just too hard. The shapes are too curvy, the slopes are changing all over the place. I found it much simpler to break it into two. So I've got an alignment that runs along the top of the stone pitching. If I go back to the standard drawing, this might be easy to describe. So I created an alignment that runs along the top of the stone pitching and along the face of the headstock, and a second alignment that runs around the inside of this little inspection ledge, inspection platform. So they're the two alignments that I've got to create in there. The other set of alignments were the ones along the headstocks themselves, and the way I approached it was to create one essentially along the centre, sort of in line with where the poles are going to be. And I've just got some insert commands for the headstock, just so I can build the shape of the headstock itself as well. So I'll come to that in a second as well. So they're the different alignments that I'm trying to pull together. So in plan view, over here, I've got an alignment that runs along the actual centre of the headstocks themselves. So there's 3 of them, 1 at each end and 1 in the middle. Alignments that run around the top of the stone pitching, and an alignment for the inspection ledge. So they're the 3 alignments. I'm going to show how I built those. But these alignments are based relative to the actual roads themselves. So I need to get my road design sorted out to have enough data to be able to create these things. Okay. So just a quick squiz at the MTF for the roads themselves. Again, just bear with me. Pretty chunky jobs, just take a little bit to open up sometimes. So, brilliant being able to create data on layers other than our design surface. So I'm able to create all these little construction strings and construction tins without interfering in the actual final design of the road itself. Anyway, so a couple of things I had to do here. One, I needed a named grade. Now this one I've defined just as a slope of 1 in 2. And the reason I went for that method rather than using links from the design is that there are no links from the design in that particular region. It's a bit of a blank because there's going to be some retaining walls built into this thing around the sitting behind the stone pitching. So there were no links to build us a name grade from, so I just put it in as a value. Okay, now the first thing then was constructing some levels up at that sort of verge, shoulder, footpath, whatever you want to call it, but up at that road level, I wanted to construct some information so I could set the height of my top of my stone pitching. Okay. Using a layer of construct bridge, just inserting relative to the footpath lengths. In this case, I actually had curb and channel and footpath. It wasn't just a shoulder like a rural. It's a more urban kind of environment. And just extended it out a little bit, just a little bit of width, normal standard footpath crossfall. And you'll see the length that I'm constructing is only 1 metre long. I've just created an alias that says, you know, the bridge inspection platform just takes a certain sort of distance along my road. And in this case, this thing is only 1 metre long. So this is creating a tiny little link just at the start of where my bridge crosses this creek here. Okay. Another one a little bit further along, same deal, just a little bit back from the limits of my bridge area. So it's only 1.5 metres long in this case. This one I made a little bit wider because I needed extra room for some guardrails, placements and so forth and so on. But just made it wide enough so that it covers the region of where I need to set my levels for this thing. And then created the strings just so I could see that they did actually get created okay. And also, I should have actually probably put this bit further, but then also created a tin from these strings. Where is it? Down here. So I created a tin from those strings so I could just drape my road alignment to the top of the stone pitching alignment to this tin to set those levels. So when I actually ran that, it gives me a tin. I'll just add them both onto both sides of the road. So it just creates these tiny little things at the start of the bridge and at the end of the bridge to give me those levels that I need to drape this part of the alignment to. So I'll bring up the editor of that alignment just so you can see how it all comes together. And profile it. Okay. So, oops, start. So that little bit of yellow you can see is sitting on top of the green of the design tin is just this tiny little patch of yellow which is sitting in the perspective view here. And in the computators, it's just a simple drape onto the tin that was created by the road function. Now, this is where things do get a little bit interesting. The alignments for the headstocks themselves are also just computated, and the levels were just hooked onto the road levels. So you do need to know just exactly how thick how big your headstocks and all that sort of stuff are. You've got to get that from your structural guys, so you can know the relationships. But in this case, the headstocks are set just as simple computators using the strings coming from the road design above at the thickness of the bridge deck, basically. Thickness from the road surface down to the top of the headstock. And the alignment was set by the bridge guys when they said where they wanted these things. So that's just a straight line, and really is nothing to it in terms of horizontal. But that headstock alignment is sitting along the centre of it, and the top of the stone pitching is obviously going to run along the face of it. So there's an offset there in horizontal, basically half the width of the headstock over here. So it is all still related together. If anything moves, it's all going to move together when you string it all together into a chain. Okay, now, so we also just used a computator to those headstock centerline alignments with a vertical offset of how far down the headstock it's going to be, which is that 200 mil above the base of it, essentially, as per the standard drawing. So computators everywhere. Everything's related to each other. And because it's a dual carriageway, hence the reason why a second computator to reference the headstock on the other bridge deck. Okay? So there are actually two separate bridge decks going in, but the spill through abutment just flows through underneath both of them, obviously. Okay? And then the floating line here is what gives me that 1-in-1 grade that goes up the outside edges of those headstocks at each end. And it can simply hook on to the end of that computator where it's running parallel to the headstock itself, and then a drape onto the tin again at the other end, sets the level so it's back up at my part level, or verge level. So a series of computators linking the road design and the headstock design to set the levels for the top of the stone pitching. Right. Okay. The next one is the one that I had to have, well, not just a serious think about, but a number of different trial and errors and different ways of doing it. And eventually settled on a method which is effectively the same as what we use for a lot of our boxing, a lot of subgrade work. And that was to find an intersection of two different slopes from two different levels. Again, oh, I've already got it open. Okay, so trying to sort of construct this inspection level, I settled on this idea of being able to intersect two different lengths. So an insert intersect here. So projecting that 1-in-2 slope down from the little construction line that I had running along the edge of the verge, edge of the footpath area, and the full depth from my design lip of curb to the edge of the road itself, using the named grade of my road surface on that right-hand side. I just abbreviated it here to road R, but this is road grade on the right-hand side, with a height type of normal. In other words, it is the true height difference running parallel to that surface grade. So by taking those two grades and two levels, I was able to create a link or a string which is at the intersection of those grades. Now, if I just pop open a cross section here, come on, profile. There we go. And I'll just extend this view a bit. So extend. Let's go give ourselves plenty of room here. Okay. So this little white dot in the cross section might be a little bit tricky to see. This little white string that's being created here, that is the projection of those two slopes. So the road surface slope at the height that I need to come down to be at that inspection level, with the 1 in 2 coming down from the projected sort of verge edge. Now, to use that link or to use that string in a computator for the alignment, the name that you give this must be unique. We can use the strings generated from the functions so long as they do have a unique name. It's only when you've got the same name string happening at various locations along the road that we then can't use them as computators, because TOSD is not sure which string you're actually talking about. Okay. So if we edit this alignment down here, if I can find him, might help if I put him in the right view. There we go. So this next alignment down, which is at the bridge inspection level, in horizontal geometry, just doing a string reference to hook on to that string that was generated by the road function. And this is where the artistic license kind of came into it. Because we can't do things like Bezier splines and French curves in a super alignment, I just came up with a couple of arcs that I thought the radius didn't look too different to the standard drawing. It was something kind of similar. So I've just floated an arc that just comes off the end of that little string into a free arc a little bit further around. Should just make that a touch bigger. Free arc a little bit further around, and then, oh, I should have put that as a commutator. Got a little bit lazy there, apologies. But basically then, just the horizontal geometry, which is just that couple of 100 mil offset from the alignment that's created or sitting at the top of the stone pitching, just for that little 1 in 1 section to come down there. So I worked out what the offset was and just manually drew it in, but we could have done that with computators as well. Okay, so 2 alignments, basically needing 2 functions now to pull it all together, and then just created 1 tin for all the stone pitching from the results of those 2 functions. So by breaking it into 2 functions and 2 alignments like this, the functions themselves are really quite simple. It's just a simple insert of a couple of links. So for the base part from the inspection level down, it was just a simple insert of the width of the inspection ledge at 850 mil, and then a batter down to another tin. And in this particular case, that tin is a realigned creek. So I've actually just constructed a sort of a platform to batter to down there of where the new creek is going to run, the levels it's going to have, but just a simple batter. Okay? And by having this curved shape and by having some decent segments to hook onto, then I could do the rotation of the crossfall from the 1 in 2, where it's perpendicular to the road, around to the 1 in 1.5 or 1 in 1, whatever you need to do, when it's running parallel to the road or perpendicular to the headstocks. So much easier to do the transition of batter slopes on that sort of shape than on a single point, which I would have to try and do if I did it all from the alignment up the top. So breaking it into 2 made it much, much simpler. Just one other little tricky bit that I used in terms of modifiers inside these. Getting this sort of little curve where the stone pitching comes back to just being flush with the end of the headstock itself. There's a neat little modifier when changing the width that you can tell it to apply a curve. Okay? So it's just a modify length modifier. We've all used that a million times, but just using this particular type of circle forward. So it's found I've set the width at the start. In this case, it was pretty chunky, 1.6 wide. A width at the end, down to 1 millimetre, so it's basically just running along the end of the headstock. And by saying the circle forward, 12D has worked out what radius it needs from start change to end change to fit a curve in there. So it gets that really nice shape to it. So again, same modifier you've used a million times, but maybe you just haven't experimented with that particular mode. But, it worked an absolute treat in here. But the rest of it is pretty much standard stuff, just inserting a link, maybe doing a bit of a modifier into it, a width, the height or whatever, just as if you were doing a road. So in the perspective view, we ended up creating the links from these two functions. Whoops. Looks like I can get across the things. So breaking into two functions just makes it so much simpler. So we get the little curvy shape where it tucks back into the headstock, down, running along. Pull them all together into a tin, and I just created one at each end. And you end up with finished product. So the real critical things there were that when I was generating links from those road functions, or generating strings from the road functions that I wanted to use as computators, they do have to be unique. That's why the names got a little bit on the long side for some of these. Whoops, not that one, this one. So depart, bridge, abutment right, approach, bridge, abutment left, and all these kinds of names to keep them unique so that I could use them in the computators themselves. Okay. And that's pretty much it. That's the whole guts of it. Again, nothing particularly rocket science in there, nothing you probably haven't used before, maybe just using it in a slightly different way. But by having it as computators, by having it all created from these functions, if something was to change with my road levels, if I needed to raise my road, then all this just sits in a chain and all just recalculates, all based on the levels come from the road itself. So there you go. Thank you very much. And Lisa, did we have any questions?
Thanks, David. We'll just, we had a few questions through. I'm just going to read out one of these here. So Dave in Queensland, so sounds like a pretty good guy, right? Based on the name and the location.
Must be.
Yeah. I said, how would you document retaining wall modelling? So what's the best way you recommend for showing retaining wall top and bottom and footing steps?
So in terms of the actual long sections themselves, I guess is what he's meaning. Put them on a plan, documenting. That's a bit of a tricky one. Essentially, they are just super alignments, one for the base and one for the top. So we can plot those strings together onto just a normal long section plot. So that's going to have all the levels and links of the different segments come out of it automatically. Getting the area in terms of quantities, getting the area of the block wall itself, unfortunately we can't just get, well, not that I'm aware of, the programmers might be able to tell me something different, but as far as I'm aware, we can't get the area of just one side or one surface of the tri-mesh. So I would just plot them both onto a long section and just do a polygon discovery to generate a polygon on the long section plot and then calculate an area from there. Just in case you guys weren't aware, there is some really cool options for getting boundary polygons of data, both in utilities ADG there's one, and even in the CAD section there's another one, there's a polygon discovery, where we just pick a point, drag it out, and it creates a polygon area. In terms of getting levels of things like the footing depths and stuff on the long section, we could do that with the offset strings part of long section plotting. Where are we? Plot long sections. So in the boxes, offset strings and titles and so forth, if we specified a model and gave it the link names that we wanted for like the thickness of the footing or the heel or something like that, we could get those levels shown on the long section as well. Anything outside that, I'll have to talk or get some more information from David. That's about as much as I understand of the question.
Sure, no problem. I think we'll save the other questions for answering by email. So thank you everyone for those. They've been great. The recording of this webinar will be available in coming days through our website and our YouTube channel. Our next 2 training webinars are Setting Up Environment Configurations on the 21st of June and Finding Things Fast in 12D Model on the 12th of July. So do keep an eye on our website for details of those, as well as our upcoming industry solutions topics. We'll also continue to keep you posted through email and social media. If you need to contact us in the meantime, our details are on the screen now. That concludes our presentation for today. Thanks everyone for attending, and we hope to see you at future webinars.